Okay, hello everyone. My name is Alina Wilson. I'm a PhD student at University of South Carolina, Department of Electrical Engineering. And my today's topic is Tunable Graphene Indium Nitride Heterostructure Diode Sensor. I'm going to start my presentation today talking about the properties of indium nitride and graphene, followed by the synthesis of the two materials. Over the years, indium nitride and graphene, they've been reported, the results for these materials be reported, but there is no source for graphene indium nitride heterostructure results. So in this presentation, we are going to show for the first time graphene indium nitride heterostructure, the device fabrication steps, and the electrical characterization. Towards the end, I'm going to show you some gas sensing results, and I'm going to conclude my presentation with a summary of my presentation. There are a lot of pollutants in environment. For example, the smoke and the fumes from the car or from the power plants, they emit the nitrogen dioxide and the sulfur dioxide, which they increase the risk of asthma, lung damage, and premature death. These gases, they are also the cause for acid rain, which they are very harmful to animals, plants, and humans. So to fabricate a device that will have high sensitivity, it will have low power consumption and portable will be ideal. Indium nitride is an attractive material because it has a narrow band gap, has high electron mobility, and is chemically inert. One very interesting property of this material is that it has surface charge accumulation, and it is important because having the electrons accumulated at the surface, when it comes in contact with the gas molecules, it either takes away or donates electrons, which results in a sudden change in the charge in the current. However, it is known that indium nitride, it does not absorb the gas molecules. So to prevent this, we are introducing another material, in this case the graphene, that acts as dual purpose, that of an electrode as well as a functionalization layer. Graphene, as we've seen previously in the other two talks, is atomically thin nature, has a tunable Fermi level, and chemical sensitivity is due to unsaturated sp2 bonds that allow us to have the indium nitride and graphene heterostructure and use the graphene as a functionalization layer. Indium nitride thin film was grown in an MOCVD growth, having the ammonia and 3-methane indium as the precursors. The 100 nanometer thick indium nitride thin films was deposited on 4 micrometer thick gallium nitride on aluminum oxide substrate. The growth was done at the temperatures of 450 to 480 degrees Celsius, with the pressures varying between 100 torr to atmospheric pressure. The graphene we've seen before is done in a CVD chamber on a pure copper foil with the temperature of 1000 degrees Celsius. The pressure was varied from 4 to 10 torr, and the precursors was the methane along with the hydrogen. The device fabrication involves few steps, and we are starting etching the indium nitride using KOH solution. This etch part will be encapsulated using an epoxy, and the graphene will be transferred on this insulating layer, and indium nitride would overlap to ensure the vertical transport in conductance between the indium nitride and the graphene layers. The graphene transfer also involves few steps. We've seen some in the previous presentation, and we start first with spin coating the copper foil with PMMA, and then we etch the bottom of the copper using oxygen plasma to remove any graphene layers, and then we etch the copper using the ferric chloride, and we deposit the graphene with the PMMA on the sample. As we can see in this picture, I know it's not a pretty picture, but this is the first batch that we fabricated. And after we deposited it on the sample, when we let it dry for 24 hours, we remove the PMMA with acetone. The last steps, we are depositing the ohmic contact on graphene and indium nitride using e-beam evaporation. To understand better the structure of this this device, we are showing here a top view and a cross-sectional view of the sample. of the device, and we can see here better the overlap of the graphene. We see here better the overlap of the graphene on the insulator and the indium nitride, and also we've seen here, as we didn't see in the previous picture, where the metal contacts were deposited on the graphene on the indium nitride thin layer, and the voltage was applied between these two pads. After fabricating the device, we are starting with the basic electrical properties and characterization. And we can see that from our IV, we get a Schottky behavior with a threshold voltage of 0.6 volts. We see a leakage current that will start at -2 volts. And in this area, we're performing our characterization that we'll show you a little bit later. So after having these great results, after having the IV characteristics, and then we see that it was similar to the previous two talks, and then we got encouraged and we went ahead and we did some sensing. First we started with water vapor, and the next one I'm going to show you for acetone. So our sample was tested for a saturated water vapor diluted 10 times in nitrogen, and we can see for indium nitride and for graphene heterojunction, we get a 5% change in current, and the recovery time is 5 seconds, less than 5 seconds. However, we tried the same thing, but this time only for indium nitride thin film, and we observed that the change in current is only 0.5%, and the recovery time is more than 30 seconds. So we conclude from this that the significant improvement in the sensitivity, in this case, and response is due to the graphene functionalization layer. We also tested the sample for 100 ppm acetone, and we get an increased change in current, and the change in conductance is 3.5%, which shows great results. So after having this preliminary results for acetone sensing and for water vapor sensing, we went ahead and we tested our sample for NO2 and ammonia. So the results for NO2 are showing here. The NO2 concentration was varied from 10 ppm to 30 ppb, and change of the two orders, and we can notice that the change in current was from more than 700% to 50% for 30 ppb. The 50% change for 30 ppb is very high, and this gives us encouragement to pursue even further and maybe get a sensitivity change for lower ppb and even for ppt. We tested the sample for ammonia gas molecules, and our concentration was varied from 100 ppm to 100 ppb, change of orders of 3, and the change in current, it was varied from 15%, less than 15%, to 3%. Even though in this case for 100 ppb the change is only 3%, is still quite significant for our device. So the sensing response to ammonia, we notice here that is in the opposite sense of that NO2, and the case is because it depends if it is acceptor or the donor type of gas molecules. The magnitude of sensing response for ammonia is much smaller than that of NO2 due to lower charge transfer per molecule for the former, for the ammonia. So in conclusion, for the first time it was demonstrated graphene indium nitride heterojunction based gas sensor, which showed excellent sensitivity to gaseous analytes down to ppb level. And compared to regular graphene chem resistor sensors, the sensitivity was orders of magnitude higher, and the donor and acceptor type molecules resulted in opposite conductance changes. For further future work, we are going to model a new device that will give us a chance to investigate the electrical characteristics even more, and also to test our samples for few level of ppb, few concentrated ppb, and go even further to the ppt concentrations. Thank you very much for your attention. If you have any questions.